In this video, we're solving a couple more examples of homogeneous polar differential equations. So I've got, this is my differential equation, also happens to have an initial condition. And this is problem 13 from section 2.5 of the ZIL textbook. It's called A First Course in Differential Equations with Modeling Applications. And I pulled this from the 9th edition of the book. Now, it might not be obvious on the surface that this is a homogeneous polar differential equation, but if I label this function m, and I label this function n, it turns out that if those two functions are homogeneous functions of the same degree, then the differential equation is a homogeneous polar differential equation. So I'm going to start this problem by verifying that the differential equation is a homogeneous polar equation. And the way we do that is by verifying that m and n are homogeneous functions of the same degree. If we can do that, then we know we've got a homogeneous polar differential equation and we can solve it with the substitution that we talked about in the last video. So m is this function, x plus y times e to the y over x. And I want to replace x with tx and y with ty. And remember, if I can replace, or if I could rewrite this, as t to some power times the original function, then that function is called homogeneous with degree of whatever that power is, that power of t. So I've got this here. Ty over tx just simplifies to y over x, the t's reduce. And then I've got a tx here and a ty there, so I can factor out my t from both of them. T times x gives me my first term, and t times y times e to the y over x gives me my second term. So that's t to the first times this function. Well, that function is m. So that's great news. So that means m is a homogeneous function of degree 1. So if n is also a homogeneous function of degree 1, then we know that we are dealing with a homogeneous differential equation. Now n is that other function, it's the one that's multiplying dy. The question is, if I replace x with tx and I replace y with ty, can this be written as t to some power times n? Well, the t's reduce again. We end up with a negative tx times e to the y over x. And I can factor out that t. And I've got t times this. Well, that's the original function. So n is homogeneous. Oops, n, not m. It's a homogeneous function of degree 1. Since this is a homogeneous function of degree 1 and this is a homogeneous function of degree 1, they have the same degree. That means the differential equation is homogeneous polar. And what that means is the original differential equation can be rewritten in this form. Since the differential equation is homogeneous polar, we can write the differential equation in the following form. dy dx equals some function of y divided by x. Now you can use this to verify that the function is the differential equation is homogeneous polar, rather than doing this if you want to. It's up to you. You kind of have to do that anyway. But I prefer this method, honestly. It makes it easier for me to see just at first glance whether the differential equation is homogeneous polar or not. So I've got x plus y times e to the y over x times dx minus x times e to the y over x times dy is equal to 0. And we want to get dy dx by itself, so we're going to divide everything by dx. The dx is reduced, and now we're here. And if I'm trying to get dy dx by itself, first I need to isolate this term by subtracting this from both sides. And then since this is multiplied by this, we're going to divide. So we will get dy dx by itself first by subtracting this from both sides, and then by dividing both sides by that. And of course, a negative divided by a negative is a positive. And since this is a monomial, you can take this term and divide it by this guy, and then this term and divide it by that guy. So we're going to have x over x times e to the y over x plus y times e to the y over x divided by x times e to the y over x. Just taking that term and dividing by the denominator and that term and dividing by the denominator. When we do that, these guys are gone. The x is reduced as well, and we get this. dy dx is equal to e to the y over x, or 1 over e to the y over x, plus y over x. And that is a function of y over x. That's 1 over e to the v, and I've got a v right there. So we've done it. We've written this as a function of y over x only. So now we want to solve this with a substitution. So we're going to let v equal y over x. Turns out that it's possible to write this differential equation entirely in terms of v and x by making this substitution. And when we do, the resulting differential equation will always be separable, which is really nice. So we let v equal y over x. And then we solve for y. That means that y is equal to x times v. And we want to think of v as a function of x. Since we're thinking of v as a function of x, when we take the derivative of y with respect to x, we've got to use the product rule. This is my first function, and this is my second function. I'm taking derivatives with respect to x. So we get derivative of the first with respect to x times the second undifferentiated plus the derivative of the second with respect to x. That's just dv dx times the first. And of course, the derivative of x with respect to itself is 1. So we just end up with v plus dv dx times x by the product rule. Okay, so now we're here, and we're looking at this differential equation at the top. Not at the very top, we're looking at this one. And our goal is to write everything here entirely in terms of v and x. So the left-hand side can be replaced by, well, it's dy dx. It's this in terms of v and x. And then the right-hand side is 1 over e raised to the v, and y over x is v by design. So we make our substitution, we do some calculations so that we can get dy dx in terms of v and x, and then we substitute. So you want to substitute for the dy dx, that's this guy, and substitute for y over x on the other side, that gives us this. To write the differential equation, the dE, entirely in terms of v and x. Now, if you've done everything correctly, this is separable. And you want to separate the variables and solve the resulting separable equation. I've got a v on this side and a v on that side. I'll subtract the v's from both sides. Oops, that's my next problem. There we go. And because I want this dv in the numerator when it's multiplying a function of v, I can't just divide both sides by dv. I want the dx to be in the numerator and the dv to be in the numerator. I want a function of v times dv on this side and a function of x times dx on this side. So to make that happen, I'm just going to take the reciprocal of both sides. And that's legal because of some theorems that we learned in Calculus 1 about the relationship between the derivatives of inverse functions. So we've got this here, and I've got it 1 over x times dx over here, and e to the v. I need all my v's on this side, so I'll multiply both sides by dv, and then by definition of the differential of x, dv, or dx dv times dv is dx, and so we get this. This is good, we've separated the variables. And you're solving a separable differential equation. So once those variables are separated, you want to anti-differentiate. Do you guys see my mistake? I see it. You see it? If you're in class, I hope you would raise your hand and tell me that's supposed to be a dv, Miss Townsend. If you caught that, that's very good, because that means you're paying attention. Got all the v's on this side and all the x's on this side. Now we want to anti-differentiate both sides with respect to the variable that's there. The antiderivative of 1 over x is natural log of the absolute value of x. The antiderivative of e to the v is e to the v plus c. And then we need to back substitute to write our answer entirely in terms of y and x, not v and x. V is just something we made up so that we could solve the differential equation. So we need to replace v with y over x. And then if possible, we would solve for y. I think it is possible to solve for y this time. Now, if I was just dealing with this original differential equation and I was asked to find a family of solutions, I would probably come to this point. I have an implicit solution right here. It's an implicit family of solutions. And then I would solve for y, which can be easily done. We can get rid of e's with logarithms. We can get rid of that division by x by multiplying by x. So this one's easy to solve for y. And that would give me an explicit family of solutions to the differential equation. But we're given an initial condition. This initial condition will allow us to find the value of c. So this is telling us that when x equals 1, we want y to be 0. We want to choose the value of c that will let x equal 1 when y equals 0, or y will equal 0 when x equals 1. We're thinking of y as depending on x instead of the other way around. So rather than finding the explicit solution first and then solving for C, I think I'm going to use this version, solve for C, and then I'll find the explicit solution. So we've got an implicit solution. We'll use the initial condition to find the value of C. And remember what this means. Y of 1 equals 0 means that when x equals 1, y is equal to 0. So we want to substitute 1 for x and 0 for y. And simplify. Natural log of 1 is 0 because e to the 0 is 1, and that's how logs and exponentials are related to each other. You've got e to the 0 equals 1 over here. So 1 plus c is equal to 0, so c must be negative 1. So that means our implicit solution is natural log of the absolute value of x equals e to the y over x minus 1. This is an implicit solution, and it's a family of solutions to the differential equation. This is an implicit particular solution. Implicit because we haven't gotten y by itself yet. Particular because it doesn't have any arbitrary constants in it. So we use the initial condition to find C, and then we back substitute. As C equals negative 1 into the implicit solution to get a particular implicit solution. I'll call this PS. PS for particular solution. Okay, now I've got my implicit particular solution. I'd like an explicit particular solution. So let's do some algebra to get y by itself. I'm just going to solve for y. So let's add 1 to both sides. And then to get rid of this exponential, we're going to take the log of both sides. And it looks a little funny, natural log of x plus 1, but it's totally fine. We could operate with that twice. And because logs and exponentials undo each other, that's just going to give you that exponent. Because those are inverse functions, that's going to get rid of that. And that's why we did that in the first place, was to get rid of the exponential. And I'm trying to get y by itself, so I'll multiply both sides by x. So right now this says y over x is natural log of the absolute value of x plus 1. And then I'll multiply both sides by x to isolate y. Okay, so this is our explicit particular solution. But we always want to find that maximal interval of existence if possible. So we've got to do a little bit of algebra here. And we have to keep our initial condition in mind. So since the initial condition was this, it says when x equals 1, y has to equal 0. Whatever interval we choose has to include x equals 1, because the solution curve has to go through the point x equals 1, y equals 0 if I were to graph it. So I want the largest interval for which this function is defined, for which the point x equals 1, y equals 0 is part of this function. Or, well, yeah, it's part of the graph of this function is what I meant. Okay, so a couple of things. Because of this natural log of the absolute value of x here, x has to be greater than or equal, or x has to be not greater than or equal to 0. Absolute value of x has to be greater than or equal to 0. So x is not allowed to equal 0. Okay, that comes from this guy. And then we've got natural log of the absolute value or of natural log of the natural log of the absolute value of x plus 1. So this expression inside this larger, this outside logarithm has to be greater than or equal to 0 the whole time. Or excuse me, it's strictly greater than 0, because we can't take the log of 0. It's not allowed. So I will solve this for x by subtracting 1 from both sides. We'll use exponentials to get rid of logarithms. And we'll have the absolute value of x has to be greater than e to the negative 1, or 1 over e, same thing. So that means if the absolute value of x has to be greater than 1 over e, it's probably been a really long time since you did this in algebra class. Here's 1 over e, here's negative 1 over e. If the absolute value of x, that's the distance of x from 0, is larger than this, that means x has to be out here or out here. Otherwise, if x is in here, its absolute value is less than 1 over e. We want it to be greater than 1 over e. So we're not allowed to include, we don't want an interval that includes x equals 0, because x is not allowed to be 0 for this function. And it needs to be either in this branch or in this branch. And it needs to include the point x equals 1, because that has to, the solution curve, excuse me, has to pass through the point x equals 1, y equals 0. Well, e is about 2.7, so this is 1 over 2.7 approximately. It's like close to 1/3, but it's not 1/3. The denominator is a little bit smaller than 3. Since the denominator is smaller, that means the fraction is going to be larger. So this is just a little bit larger than 1/3, but x equals 1 has to be over here somewhere. So it looks like our interval of existence starts at 1 over e and goes to infinity, and that's going to include x equals 1. So we've got an explicit particular solution on this interval. That's the solution of this original differential equation. If you're saying to yourself, what on earth does that mean? Well, it means if you take the derivative of y with respect to x and you replace y with this function here, y is going to satisfy this differential equation.